As a last piece of physics today, I would like to introduce electrostatics in proteins to you. You probably know what the potential of interacting charges is. 1 over 4 pi epsilon 0 epsilon r, where epsilon 0 is the permittivity of free space and epsilon r the relative permittivity, multiplied by the product of the two charges divided by the distance between them. In water, epsilon r is a high number, and that means that the potential will be much lower than in vacuum. The reason for that is that if you place a charge or two charges in water, water molecules will instantly screen that. In this case, it's a positive charge, so they're going to screen that by turning their oxygens toward it. And because waters have fairly high partial charge, they're going to be efficient in screening, and the entire water molecule can rotate, which is going to orient this dipole to screen things very efficiently. And that's the reason for the high value of 80 for the relative permittivity of water. The protein interior doesn't work this way at all. The side chains are not completely free to rotate. They don't have large charges. But rather, you're going to have an epsilon r inside a protein that's almost like oil, 2, 3, maybe 4. And that's going to make a very significant difference. So if in water, these two unit charges at the distance of, say, 3, 4 angstrom, they might have an energy in the ballpark of, well, 1, 2 kilocalories per mole, maybe 3. I haven't done the math. The same charges placed inside a protein, well, that's almost like placing two charges in oil. And this oil will not hide them at all from each other. They're going to see almost everything. The reason why it's not 1 is that there is some electrons here, and the electrons, there are some electrons here, and the electrons will shield it, but not very efficiently. What that will mean that two charges inside a protein at the same distance might have an interaction energy of, say, 40 kcals per mole. That's gigantic. Remember, you should compare it to the unit, which is 0.6 kcals per mole. E raised to 40 divided by 0.6, that would be, say, roughly 50 or 60, right? That's a large number. So large that it's in my eat my left shoe territory. Meaning, free charges will not occur inside proteins. We do not expect to see them there. Expect is the keyword. There are exceptions, and we will come back to that when we look at membrane proteins, and in the next slide, actually. So how can we introduce proteins? Charges in proteins, because occasionally we need them. Well, there are some charged amino acids, but in fact, these amino acids are not really charged. They're so-called titratable amino acids. And by titratable, we mean that the side chain has an acid or a base. And what that means is that they might be either positively or negatively charged at room temperature, but depending on the pH of the surrounding, they can either take up or release a proton to become neutral instead of charged. That is not a free lunch. It will not happen without paying, but it turns out that it's significantly cheaper to pay to neutralize amino acids. That might be a handful of kcals rather than taking that charge and bringing it to the interior of the protein at any cost. So whenever we see so-called titratable amino acids inside a protein, it's a very good bet to assume that they might be neutral after all. But even there, we have some exceptions to that rule for membrane proteins.